Okay, we're now going to look at what happens when changes are made to the system that's in equilibrium. Remember, system in equilibrium involves a system where no substances can be added, just the energy can flow in and out. And looking at this, we're going to look at a principle called Lechatellier's principle, which states that for a system that's in equilibrium, if a stress is applied, that's going to be a change in concentration, change in pressure, change in temperature, applied to the system, then the system moves to oppose that stress, that change. So it basically just will do the opposite to what you've done to the reaction. So if it's temperature, if I heat it up, the system will look to cool down. If I add more of A and B, the system will look to get rid of A and B. If I add more pressure, the system will look to relieve the pressure. While Lechatellier's principle is a nice statement, it effectively states the obvious, okay? It's just common sense happens, and I'll try and explain that as it goes through the video, okay? So we're going to first look at concentration. What happens if there's a change in concentration to our equilibrium system? Well, concentration is just a number of moles of particles per unit volume. So let's have a look. If I add more A, so if I increase the amount of A, for example, what's going to happen? Well, Lechatellier's principle tells me that the system will look to oppose the increase in A, so it'll look to reduce A. So the system looks to reduce the amount of A. How does the system reduce the amount of A? The only way it can reduce the amount of A is by reacting A with B. Well, if A reacts with B, then surely you produce more of C and D. Well, if you produce more of C and D, then position of equilibrium shifts to the right. So, just to recap, equilibrium only happens when you've got a closed system. If we add something to the system, it's no longer in equilibrium. So let's just say my position of equilibrium was right here to the left-hand side, and suddenly I add in more of A. What's going to happen? Well, A is going to react with 2B molecules, and it's going to produce more of C and D. If more C and D get produced, then that just simply moves to the right-hand side. We don't know how far it moves because we don't know how much of A has been added. But all I know is that the system will move to produce more C and D. Come back to why this is just stating the obvious. Well, if I add more particles of something, then there's more of those particles available to react with B. So B has a greater chance of colliding with those particles and getting successful collisions to produce more of C and D. So by adding more of A, essentially, common sense tells us that B will have better chance of reacting with it, and so you must produce more of C and D. So this is going to happen until system will then re-establish the equilibrium. It just so happens that the equilibrium now has moved over this side now, this purple line. What happens if I take away A? So if I reduce A, well, the system will look to increase the amount of A. So if I start taking out A, then B won't have as many particles to react with. So this reaction here, this forward reaction, will happen a lot slower because B won't have as much to react with. So therefore, this backward reaction happens at a much faster rate. So look, system looks to oppose the change always. Now we're going to look at something else. We're going to look at pressure. Pressure just involves gaseous systems, so where you've got gases of reactants and products, so you've got gases involved. What is pressure? Pressure is caused by particles colliding against the boundaries of the container. Okay, so we can imagine if we've got a system, let's say you've got a reaction happening in a balloon. If I put pressure on the balloon, i.e. I squeeze it, I reduce the volume and therefore I increase the pressure. If I increase pressure in an equilibrium, what is the system going to do? It's going to try and reduce that pressure. How does a system reduce the pressure? Well, if pressure is caused by particles colliding against the sides of the container, the system is going to favour the reaction that produces the fewest number of particles, or the fewest number of moles of particles. So, if we've got a system where we produced fewer number of particles, the system will look to favour that reaction. So let's look at that here. Let's say I increase that arrow there. If I increase pressure, system will look to decrease pressure. The only way the system can decrease the pressure is by favouring the reaction that produces fewer particles. So in this case, the reaction that's favoured is a forward reaction, because there are 3 moles of particles here, or 3 particles, and on the right here we've only got 2. So the only way the system can relieve the pressure is by favouring the reaction that produces fewer molecules. So when gases are involved, if I increase the pressure in the system looks to decrease the pressure, therefore favours the reaction that produces fewer molecules. So in this case, position of equilibrium will shift to the right. Now let's go back to the common sense methodology to think about it. If you want to just stick with Lechatellier's principle, that's fine, that will work. But if I have my balloon and I've got gas particles reacting, if I squeeze the balloon, I'm increasing the pressure. What that basically means is I'm pushing these particles closer together and I'm pushing these particles closer together. Well, if I'm pushing these particles closer together, I know that for every A there's 2 of B, and for every C there's 1 D. So there's a greater chance of A and 2B reacting by reducing the volume, because I'm pushing these closer together than there is just of C and D, because you've got more particles of A and 2B. So we're now going to look at the last part, which is temperature. Temperature is caused by the kinetic energy of the particles. We know that temperature is related to energy. Therefore, we're going to be looking at this thing here, the energy change in the reaction. What this means, as I explained at the very start, delta H is negative. Therefore, forward reaction is exothermic. For more on that, see the energetics video. The backward reaction is endothermic. So, on going from A to B towards C and D, the forward reaction, basically as this reaction happens, energy is released to the surroundings. Therefore, temperature increases. If I look at the backward reaction, I'm going from C plus D to A and B. There's a decrease in temperature because energy is taken in from the surroundings to allow this reaction to happen. Okay, so inside the yellow box here, if the delta H is negative, that means the forward reaction is exothermic and it releases energy. Let's have a look at the system now. If I increase the temperature in the system, well, according to Lechatellier's principle, system's going to look to decrease temperature. How does the system decrease temperature? It favours the endothermic or the backward reaction, because we know that the endothermic reaction takes in heat from the surroundings or takes in energy from the surroundings, and so the temperature gets decreased. It's the only way the system can reduce the temperature. So it favours the backward reaction, that's endothermic. Therefore, position of equilibrium shifts to the left. Likewise, if I actually reduce the temperature, so if I decrease the temperature on this whole thing here, the system's going to want to increase the temperature and therefore favour the exothermic reaction. Now, what effect does the catalyst have on the reaction? Catalyst only speeds up the rate of both reactions at the same, but equilibrium just gets established a bit faster. So we've looked at the factors that can change the position of equilibrium. There's some really good clips on YouTube using nitrogen dioxide, dinitrogen tetroxide, as both are different colour. There's an equilibrium established between the two. There's also really good experiments you can do with potassium dichromate and cobalt chloride. So both of those systems are separate and exist in equilibrium systems themselves, involving species that have different colour. So it's really handy actually just to add a few chemicals and what you can see the colour change. And you can see Lechatellier's principle. So there's clips on YouTube to look for that. So key things to know from this: a dynamic equilibrium is where we have a closed system and the rate of the forward reaction is equal to the rate of the backward reaction. We know that the reactions are happening. When they happen at the same speed, then the system is in equilibrium. If you make a change to the system will adapt so as to oppose the change, and therefore the position of equilibrium is likely to alter. Remember, that change is a change in temperature, pressure, or concentration. In another video, I'm going to look at the industrial applications of Lechatellier's principle and the compromises that are needed to take place, specifically in the Haber process and the contact process. And in another video, I'm going to talk a little bit more about the mathematics behind it and how it's all related to an equilibrium constant called Kc.